let's look at solving for potential difference, current, and resistance in circuits. And we'll start with series circuits. And let's start out that with the rules that govern series circuits. So let's put that down. Well, we know that the equivalent resistance of a combination of resistors in series is the sum of the resistances. Okay. We also know that in a series circuit, the current is the same through each resistor. All right. Another fact, which we haven't mentioned yet, is that the total potential difference across an entire combination of series resistors is the sum of the potential differences across each. So if I have 3 resistors, and there's 2 volts across the first resistor, and 3 volts across the second resistor, and 2 volts across the third resistor, the total potential difference across the total combination is 2 volts plus 3 volts plus 2 volts, or 7 volts. All right. So with that in mind, let's draw a series circuit. Let's make it a battery giving 5 volts of EMF, and then a 2 ohm resistor, a 3 ohm resistor, and a 5 ohm resistor. So the way to attack this, what I suggest, is create a little chart. Make a chart where you have one column for the potential difference across every element, one column for the current, and one column for the resistance. And then the rows, each row is going to be for a different resistor. So let's say we've got R1, R2, R3. So each one gets a different row. And then at the bottom, I'm also going to put the total. That row is going to be called total. So I'll show you what I mean by that in just a moment. But we're going to put in all the information that we have. So R1, we know the resistance. R2, we know the resistance. R3, we know the resistance. For the total, well, we know the total potential difference across all the resistors because that's the potential difference provided by the battery. So we know the potential difference across the total is 5 volts. So we can put that in there. Okay, now we can apply the rules. Let's see what else we can figure out. Well, we can figure out the total resistance in the circuit. Because the total resistance in the circuit, well, these are 3 little resistors in series. The equivalent resistance, the total resistance that they provide, is the sum of their resistances. So it's 2 ohms plus 3 ohms plus 5 ohms, or 10 ohms. That's the total resistance. All right. Now let's see what we can figure out. Well, if I know the total potential difference and I know the total resistance, I can figure out the current using Ohm's law. Because if I have 5 volts across 10 ohms of resistance, the current has to be, we'll do a little bit of math, the current has to be 0.5 amps. Okay, now what else can we know? Well, one of the rules is that the current has to be the same through every resistor. Well, if there's 0.5 amps flowing here, that has to be the same current flowing through everything. So I know the current through all of my resistors. Same current flows everywhere in a series circuit. And let's see, now what can I find? I can find the potential difference across every single resistor because I know the current through every resistor and the resistance of each resistor. So I can use Ohm's law. So for instance, R1, the potential difference across R1, let's see, that's equal to 1 volt. And R2, well, that's equal to 1.5 volts. And R3, that's equal to 2.5 volts. All right. Now, there's another rule, and that last rule that we did not apply is that the potential difference across each resistor, if you add it up, it's equal to the total potential difference across all the resistors. So look at what we got. Add up those potential differences across all the resistors. 1 volt plus 1.5 volts plus 2.5 volts. That's 5 volts. Hey, that's what's in the bottom column. All right. That takes a little bit of practice. And you're not always going to be able to follow those exact steps. And in different problems, you'll be given different information. But you're always applying those same rules for a series combination of resistors. Now let's look at a parallel combination. So let's review what we know about parallel. In a parallel combination, the potential difference across every resistor is the same, and the current will be different. We also know that an equation for the total resistance of that combination called the equivalent resistance, and that equation looks a little frightening. There is one other thing we know, and that is that the current that flows into the combination is going to equal the sum of the currents through each resistor. And the way you can think about this is, imagine the current flowing into this junction. 3 currents are going to flow out. So one current goes in and then it splits into 3 parts. Well, that one current that goes in has to be the same, or has to equal the sum of each of the currents that go through the resistors. And then after they pass through the resistors, they go to this junction, they all combine back together. So all three currents have to add up again to equal the current that comes out of that combination. So another way to say that is, in a parallel combination, the currents through each resistor add up to the total current that enters and leaves. Okay, so let's draw a parallel circuit. Let's do the same elements: a 5-volt EMF, 2 ohm resistor, 3 ohm resistor, 5 ohm resistor, 1, 2, and 3. So we'll make the chart again. Each resistor gets a different row, and at the bottom we'll put the total. If we do that, let's fill in the information that we know. Well, we know the resistances of each resistor. We know the total voltage, the total potential difference supplied. What can we say next? Well, we know that in a parallel combination, the potential difference across the resistors is the same. Well, the potential difference across the resistors is what's given by the EMF here, which is 5 volts. So every resistor has 5 volts across it. Okay, once we know that, we can do everything pretty quickly. We can use Ohm's law to find the current through each resistor. So we have 2.5 amps, 1.67 amps, and 1 amp. And we know that the total current that's flowing is going to equal the sum of all of the currents through each of the resistors. So the total current is 5.17 amps. And now if we want to know the total resistance that's in the circuit, which is the same as the equivalent resistance of all of this combination, we have 2 ways to find it. We could use Ohm's law to find the equivalent resistance, or we can use the resistance equation. And either way you do it, you get the same answer. Let's look at another example of a series circuit. So I'm going to draw a series circuit here. Here's a battery with an EMF of 1.5 volts. Let's say R2 is 1 ohm, and we don't know what R3 is, but the current through the whole circuit is going to be 0.1 amps. So let's attack this in the same way. Oh, but first, the question that I'm asking. I want to know the potential difference across R2. I want to know what the resistance of R3 is, and I want to know the total resistance in the circuit. All right. Let's make our chart. V, I, R, R1, R2, R3, total. Let's put in the information we know. We know the resistances of R1 and R2. We know the total EMF, the total potential difference. And we know the current through the circuit. And this is a series circuit, so the current is the same everywhere. So we can fill in that entire column. Once I do that, well, let's see. I can solve for a couple things. I could solve for the potential difference across R1 and R2. Let's do that. Okay. I can solve for the total equivalent resistance in the circuit. And I know that all my resistances, resistance R1, R2, and R3, have to add up to the total resistance. So that means I can find the resistance of the third resistor. It's 9 ohms. All right. And I can find then the potential difference across R3. So the potential difference across R2, 0.1 volts. The resistance of R3, 9 ohms. The total resistance across that combination of resistors, 15 ohms. And lastly, let's do one more parallel circuit. So I'm going to draw it. It'll look a little bit different than the parallel circuit we saw before, but it still counts as parallel. The current goes in, branches, comes back together, goes back to the battery. And let's make it a 8-volt EMF battery. Let's say we don't know the resistance of the first resistor, but the current flowing through it is 1 amp. And then the second and third resistors both have resistances of 4 ohms. So let's make our chart. And let's fill in the information that we know. All right. Okay. One of the facts we know about a parallel circuit, parallel combination, is that the potential difference across every resistor is the same. Well, every resistor has the same potential difference across it as the battery. So every resistor has 8 volts across it. So we can fill in that column. Now that I've done that, well, I can use Ohm's law to fill in the resistance of the first resistor and the currents of the second and third resistor. Next, I know that the current through each resistor in parallel, it adds up to the total current. So I can find the total current coming out of that combination. And then the only thing I don't know is the equivalent resistance of the resistor, or of the combination of resistors. So I can do that in 2 different ways. I could use Ohm's law, or I can use the equivalent resistance equation. Either way, I get 1.6 ohms.